Alright, continuing on. Next problem, X-ray wavelength of 7.32 10 to the negative third nanometers. So this one, we're going to have to convert. So remember, we have Mega King Henry died unexpectedly drinking chocolate milk up near Punahou. We have 6, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4, negative 6, negative 9, negative 12. And of course we're going from nano to unit. So the first thing I'm going to do is convert 7.32 times 10 to the negative third nanometers. So meter is a bigger unit. And then between 0 to negative 9, the difference in the powers of 10 is 9 tenths. So 10 to the 9th. So let's see what that gives me. 7.32e negative 7, or sorry, negative 3. Negative 3 times 1 divided by E1, E9. Okay, so that gives me that number. Okay, that's my wavelength in meters. So now I can plug it into the light equation. 3 times 10 to the 8 meters per second over 7.32 times 10 to the negative 12 meters. 3e8 over answer. Okay, so that's going to be 4.1, or yeah, 4.1 times 10 to the negative, or 10 to the 19th hertz. Then I'm going to put it into this equation. So energy is equal to 6.626 times 10 to the 34 joules times second, multiplied by 4.1 times 10 to the 19th hertz. That's going to be equal to 6.626 e negative 34. 2.772 times 10 to the negative 14 joules. Okay. Next, we have frequency, calculate its energy. So again, notice since I'm already given frequency, I can plug it straight into this guy. So E is equal to 6.626 times 10 to the negative 34 joules per second times my frequency. That's going to be equal to 6.626 e to the negative 34 multiplied by 2.68 e6. Okay, 1.78 times 10 to the negative 27 joules of energy. Alright, great. Next, calculate energy and the wavelength of a photon with a frequency of that. Okay, so let's do energy first since that one's easier. E equals 6.626 times 10 to the negative 34 joules second. And the frequency, you can plug it straight in. Hertz. So E is going to be equal to 626 e to the negative 34 times 6.165 e to the 14. Oh. There we go. Okay, so the energy is 4.08 times 10 to the negative 19 joules. And then we also want wavelength. So I'm going to be using this equation. C is equal to lambda nu. C is 3 times 10 to the 8 meters per second is equal to, solving for lambda, our frequency is 6.165 times 10 to the 14th hertz. So divide both. I want lambda by itself, so I'm going to divide by that. 6.165 times 10 to the 14th. Okay, and my wavelength is going to be 3e8 over 6.165 e14, which would be 4.87 times 10 to the negative 7 meters. Okay. Alright, continuing on, a couple more. Calculate frequency and energy. Blue light wavelength of 400 nanometers. So again, got to use our conversion factors. Going to take 400 nanometers, convert it into meters, so 1 meter. And then again, it's the difference between meter, which is a U, and nano, which is 10 to the negative 9. So the difference between negative 9 and 0, 9 minus 0 is 9. So it's 10 to the 9th power. 400 times 1 divided by 1e9. 4 times 10 to the negative 7 meters. Now I can plug it into this, so speed of light divided by my new wavelength in meters. Frequency is going to be 7.5 times 10 to the 14th hertz. And then lastly, energy, 6.626 times 10 to the negative 34 joules per second, times by 7.5 times 10 to the 14th hertz. And it's going to be equal to 6.626, oops, e negative 34 times 7.5 e 14. E is equal to 4.97 times 10 negative 19 joules. Okay. Okay, next one. Wavelength energy of light, frequency of 1.5 times 10 to the 15th. So it's very much like number 12. So do energy equation first, 6.626 times 10 to the negative 34 joules second, multiplied by the frequency, 10 to the 15th hertz. So let's see, 6.626 e negative 34 times by 1.5 e to 15. Okay. Energy is equal to 9.39 times 10 to the negative 19 joules. And then I want to find the wavelength. So 3 times 10 to the 8 meters per second is equal to wavelength times the frequency. So again, I want to isolate lambda, so I'm going to divide by 10 to the 1.5 times 10 to the 15 to get lambda by itself. Two times 10 to the negative 7 meters. Okay. Next one, photon of light, wavelength of 0.5 centimeters. Calculate its energy. Okay, so notice this one is centimeters. So if I look up here, that's right here, centimeters to meters. So I'm going to take 0.05 centimeters. Centimeters goes on bottom, I want to cancel it out. Meters goes on top. And then how many tens between unit and centi are 0 and 10 to the negative 2? That would be 2. .05 times 1 divided by 1 e2. 5 times 10 to the negative 4th meters. And then have to get, to get the frequency. So use that guy. So 3 times 10 to the 8 meters per second over 5 times 10 to the negative 4 meters. That's my wavelength. 3e8 over 5e negative 4. Okay, so that's equal to 6 times 10 to the 11th hertz. And then lastly, energy is equal to 6.626 times 10 to the negative 34 multiplied by 6 times 10 to the 11th hertz. Okay, so the energy is 3.98 times 10 to the negative 22 joules. Okay, so that's that. Okay, isotopes. So remember, isotopes are elements that have a differing number of neutrons than normal. So we're going to look at these three and kind of get some information out of them. So C is carbon. 6 refers to the atomic number, which is the number of protons. So notice they all have 6 protons. If we change the number of protons, we change the identity of the element. So if we add a proton, it's going to change it to nitrogen. 12, 13, 14 are the atomic mass, or protons and neutrons. So protons and neutrons would be 12, protons and neutrons would be 13 and 14. Okay, complete the chart. So atomic mass. So notice in this notation, whatever that number is atomic mass. So 37, 17, 235, 238, 10, and 11. In order to know the atomic number, you will probably have to check your periodic table unless you have it memorized. So I'm going to check out my periodic table. Okay. So we're going to look for potassium, K. Okay, so notice potassium is 19. Atomic number is 19. Oxygen, O. Atomic number is 8. Okay, uranium. So here, 92. 92. Remember that the atomic number doesn't change as long as the element stays the same. Boron is here and it's 5. Okay. So number of protons is basically the atomic number, so that's easy. Number of neutrons is the mass number minus the atomic number, or the number of protons. So 37 minus 9. Is 28. 9. 235 minus 92, 143. Actually, whoops. Oh yeah, no, I did it right. This is 235. Keep doing it. 235. And then 238 minus 92, 146. 10 minus 5, 11 minus 5. And then we're going to talk about ions later, but as long as it's not an ion, as long as there's no charge, which none of these have a charge, none of these are ions, it's going to be same as number of protons to give it a neutral charge. Okay. Okay, we kind of did some of these problems already, but just going to do them again. We have two isotopes. We have 151 and 153. So 151 is the atomic mass and abundance is 48%. So I put in a decimal form and we add that to the next guy, 153 times 51%. Okay, remember that it's out of 100, so I've got to move the decimal over 2 times. Let's punch this into our calculator. Add that to 151 times 0.4803 added to 153 times 0.5197. That's gonna give me 152.0 pretty much. Yeah, 0.0. Okay, AMU. Okay, next guy. Ooh, 4 isotopes. Okay, so we got 84 times 0.5. Well, 0.5%. Okay, be careful. 0.5% is that. Whew. And we got 86 times 0.99. Oh, 0.09. Okay, 0.9 would be 90%. We got 87 times 0.07%, or 0.07%, and then 88 times 0.826. Okay, so we're gonna do that. This is strontium. So long guy, 84 times 0.005 added to 86 times 0.099 added to 87 times 0.07 added to 88 times 0.826. That's going to be equal to 87.7 AMUs. Okay. And notice, if it's not even close to any of these numbers, you might have done something wrong. Okay, another light equation. We have micrometers now. So I'm gonna do my Mega King Henry died unexpectedly drinking chocolate milk up near Punahou. 10 to the 6, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 6, negative 9, negative 12. Okay. And this is a hard one. This, you won't see this on your tests. This is a AP Chem problem because notice also kilojoules. So I'm trying to find the wavelength of light. Okay. Actually, wait, number of photons. Okay. So actually, I don't know why this problem is in here. We didn't even cover number of photons. Maybe you'll cover that in AP Physics. Don't worry about number 20. Okay, number 21. Total energy. Okay, again, sorry. This is, we didn't talk about number of photons, so we are not going to do that. Okay, name the scientists. Chadwick. We got plum pudding model with Thomson. Thomson does electron as well. Goldfoil is Rutherford. Atomos is Democritus. Densely positive nucleus, that's Rutherford. Energy levels is Bohr. And discovered the atom combined Das Dalton. Okay, models. So Dalton was the first one. Looks like this. Then you have Thomson. Plum pudding model. Then you have Rutherford. Densely positive nucleus with electrons orbiting around. Then you have Bohr. And the planetary model. So again, positive nucleus, but electrons are orbiting in layers. Okay, amplitude is B. Okay, actually, sorry, whoops, made a mistake, it's not B. D would be the amplitude. Okay, from the midpoint of the wave to the crest. And then A would be 2 wavelengths. C is actually the wavelength. Okay, A would be wavelength times 2. There's 2 crests. Actually 3 crests. Okay, so C and D. Okay, what happens to the wavelength of a wave if I increase the frequency? Remember, they're opposites, they're inversely related. So if I increase the frequency, wavelength is going to go down. Okay, so if I increase the frequency, right, wavelength goes down. If I have a very low frequency, wavelength gets really big. Okay, so decrease. What happens to energy? So energy and frequency are directly related, which means if I increase the frequency, energy is also going to increase, vice versa. Okay, highest and lowest energetic particles. So again, if you remember that, right, notice that wavelength, if I'm comparing wavelength, this is a big wavelength, big wavelength, this is small, which means that this has a small frequency. Okay, small frequency, big frequency, which also means that this has big energy, small energy. Okay, so you got to know this relationship between frequency, wavelength, and energy and frequency. This is indirect, opposite. So highest would be gamma, energy, and lowest would be radio. Okay, same thing with the colors. Violet is the highest energy, red is the lowest. Okay, flame test lab. So we had this example for the flame test lab. You need to be able to explain that when you energize an electron, and this is kind of a misleading picture. Maybe not. If you had an electron right here, which usually it's not a nucleus, usually it's right here. Let's say you had an electron and you energized it. Okay, it's going to increase its energy. It's going to jump further out. It might even jump farther than that. But it's very unstable, doesn't like that, so eventually it's going to fall back down. It might fall there, it might fall to the second level or the third level, and when it does that, and there's a picture right here that shows it, you get your different colors. So the amount of electrons, the differing amount of electrons produce different amounts of photons that are releasing energy. That's why you get all the different colors. Okay, but the key is that when you heat it, right, or you energize, if the sun energizes it, it increases the energy of the electron. And then when the electron returns or loses energy, it releases a photon of light. Okay, photon of light. And that's how we get the pretty colors. Okay, so thanks so much for joining me with this review. Again, you might want to work through it a couple times or work through it enough so that you can do it pretty flawlessly and in your sleep. So that will be that'll prepare you for your test. All right, good luck, Godspeed, may the force be with you, and thanks for joining me on this review.